Hello everyone, welcome back to another physics video. I'm Physics Michael, and today we are continuing our exploration of stationary waves. We will look at practical applications of stationary waves, including how they work in data streams and air columns, and learn how to measure the speed of sound in air. Let's get started. First, let's look at the stationary waves formed on a data stream. When both ends of the string are fixed, we can create a series of different stationary waves with two nodes at both ends, just as shown in the figure below. The simplest one with just one loop is called the fundamental, or first harmonic. It has a wavelength of 2L and a frequency of f0. This is the lowest frequency and the largest wavelength of stationary waves formed on the string. Then we can create the second harmonic with two loops, which has a wavelength of 1L and vibrates at twice the fundamental frequency. This is because the speed of the wave on the string is constant, so the frequency is inversely proportional to the wavelength. And similarly, the third harmonic with three loops vibrates at 3 times the fundamental frequency. Let's solve an example about data string harmonics. Imagine we have a data string with both ends fixed is vibrating. The largest wavelength of stationary waves formed on the string is 50 centimeters, and the wave speed along the string is 5 meters per second. What is the frequency of the third harmonic of the string? Let's solve this step by step. First, let's find the wavelength of the fundamental. It is just the largest wavelength of stationary wave formed, so the fundamental wavelength equals 50 centimeters, or 0.50 meters. Now we can find the fundamental frequency. Wave speed divided by wavelength gives us 5.0 divided by 0.50, which is 10 Hz. Finally, the third harmonic is 3 times of the fundamental frequency, so it is 3 times 10, which equals 30 Hz. Now let's look at stationary waves in air columns. These are fascinating because they are how wind instruments make music. We'll look at a tube with one open end and one closed end. Just like with strings, we have a simplest one called fundamental, but it has only one half loop with an antiload at the open end and a load at the closed end. And it has a wavelength of 4 times L and a frequency f0. This is also the lowest frequency and the largest wavelength of stationary waves formed in this kind of air column. But here's where it gets interesting. The harmonics works differently in air columns. After the fundamental, the next harmonic has 1.5 loop, so it has a wavelength of 4/3 of L. Since sound speed in air is constant, the frequency should be inversely proportional to the wavelength, so the frequency is 3 times the fundamental. We call this the third harmonic. And similarly, the fifth harmonic has 5 times the fundamental frequency. Here's a practical example. A stationary sound wave is formed in an air tube that's 1.0 meters long. Using a microphone, we detect a series of maximum and minimum points as shown in the figure. The sound frequency is 416 Hz, and what is the speed of sound in air? To solve the question, let's first draw the wave pattern in the air tube. Maximums are antiloads and minimums are loads, so we can draw the wave pattern with 2.5 loops in the tube, as shown here. 2.5 loop means 2 half wavelengths and a quarter of wavelength. So it's easy to note that 1.0 meter equals 1.25 wavelengths. So the wavelength is 0.80 meters. Now we can calculate the speed of sound. Frequency times wavelength gives us 416 times 0.80, which equals 333 meters per second. Here's another interesting example. We place a loudspeaker that produces a 256 Hz load above a water-filled tube. As we lower the water level, we hear two loud sounds when stationary waves are formed in the tube, just as shown in the figure. The height difference between these loud points is 65 centimeters. We need to calculate the speed of sound in air again. As you can see from the wave pattern, the height difference between two loud sound heard points is just 1/2 wavelength. So the wavelength is twice the height, 130 centimeters or 1.30 meters. Then multiply by the frequency. 256 times 1.30 gives us 333 meters per second. Let's summarize what we've learned today. The fundamental or first harmonic is the lowest possible frequency and the largest possible wavelength for a stationary wave formed in any system. We can find maximum and minimum using detectors like microphones, and the stationary wave pattern can be drawn by their positions. When looking at stationary wave patterns, one complete loop represents half a wavelength, a half loop represents a quarter wavelength, and once the wavelength is determined, we can use the wave equation, wave speed equals frequency times wavelength, to get the wave speed in the media. That's all for today's video. Thanks for watching. I hope you now understand how stationary waves work in real-world applications, and how we can measure sound speed using air tubes. I'm Physics Michael, and I will see you in the next video.